Let's talk about specific heat then. The definition of specific heat is the amount of energy or heat needed to raise the temperature of exactly 1 gram of a substance by exactly 1 degree Celsius. So that should sound actually very familiar to you because that's the exact same definition that we gave for the calorie, right? The difference is that instead of just any substance, it's actually water, H2O, right? And the number we gave there for the calorie uh, in joules was 4.184 joules. So it turns out that 4.184 joules is the specific heat of water. So it's pretty much all the same thing, or it is the same thing, right? But we can actually calculate the specific heat for any substance, right? Using this equation that we have right here to the right. So let's do a little bit of an example here, right? We have 24.8 grams of some metal that we don't know what it is, and it's absorbing 275 joules of energy. The temperature change that occurs, right, when it absorbs that energy is 20.2 degrees Celsius to 24.5 degrees Celsius. So we just need to use this equation to figure out what the specific heat of this unknown metal is. We have the heat, which is right there. This is the heat. We have the mass of the stuff, whatever it is, right here. And we also have this, delta T, which is the change in temperature. That's the 24.5 degrees Celsius that came from the 20.2 degrees Celsius, right? That change in temperature. So let's go ahead and plug in the equation. Specific heat then equals 20, or 270 rather, 5 joules over 24 grams, 24.8 grams, times the change in temperature, which is 24.5 degrees Celsius, minus 20.2 degrees Celsius. Some quick and easy arithmetic here tells me that this part in the parentheses, 24.5 minus 20.2 equals 4.3 degrees Celsius. That's the delta T, or the change in temperature. We'll put the rest of it into the calculator to figure the rest of that out. Let me switch over to the calculator view so you can see what I'm doing. There we go. Right? So it's really important here that you use your parentheses because we definitely want the calculator to know to do this arithmetic, this subtraction of the delta T, or change in temperature, first before it does the multiplication in the denominator, and then before it does the division with the numerator, right? So this is how we would type it in. 275, right, divided by, this is where we start opening the parentheses up here, 24.8, and we want that to be multiplied by, we'll want to open this parentheses again because we want to have the stuff in here to happen first. Open parentheses 24.5 minus 20.2, and that should be it, right? So if you look at the calculator the way I typed it in, if we're using our order of operations, we know that the parentheses are going to tell the calculator to do the arithmetic in here first, the 24.5 minus the 20.2 first, and then it will multiply the 24.8 grams, then it will divide with the 275. And our answer that we get from the calculator is 2.578 dot dot dot, some numbers, right? Well, we have to use our sig figs here. There are 3 sig figs here with the heat. The mass has 3 sig figs as well, but the change in temperature only has 2 sig figs, right? So we're going to have to change this to be 2 significant figures. How do we do that? That will be 2.6, right? And the reason why is because if we look at the 7 here, the 7 actually rounds the 5 up to 6, and that's why we have 2.6, right? That's why we have 2.6. Good, good. And then also don't forget the units, because sometimes I even forget the units here. I was just thinking about that. This unit's going to be joules per gram Celsius, which makes sense because that's 2.6 joules for every gram for every degree Celsius, right? That's why it's the unit. Very interesting stuff. So, let's try another example, right? Here's a chart of known specific heats that people have done experiments on and figured out, right? So now we want to use the specific equation to calculate the energy in kilojoules needed to heat up 255 grams of copper from 24 degrees Celsius, which is basically room temperature, to 185 degrees Celsius, right? So how do we do that? Again, we have our specific heat equation. Over delta T, right? So let's make things easier on ourselves and do the delta T part first. So delta T here equals 185 degrees Celsius minus 24 degrees Celsius, right? And that equals 161 degrees Celsius. And now that we have this number, we can go ahead and do some dimensional analysis again, actually. It looks a lot like it, right? So now SH, for specific heat, equals the 255 grams, right, times the change in temperature, which was the 161, times the, put a unit there, don't forget the unit, times the specific heat of copper in joules, which we find to be there, and that is 0.385 joules. And then we have to actually convert it to kilojoules because the answer needs to be in kilojoules. So to convert joules to kilojoules, we'll put our conversion right here. For every 1 kilojoule, there is 1,000 joules. And I'm sorry, but I just blocked all that stuff out with my face in the calculator. So I'm going to go ahead and show you that, or just hide myself in the calculator real quick so you can see what I'm writing here. So this is basically like a dimensional analysis problem we did before when we were doing unit conversions, right? Because you can think of the 255 being over 1, the 161 being over 1, and the specific heat of copper being over 1. So all you have to do is multiply all the top numbers, the 255 times the 161 times the 0.385 times 1, and then divide all of that by 1,000. Right? So I'll do it on the calculator over here. It's simple input. And the answer I get is, from the calculator, is 15.806, right? Again, we have to do our sig figs, right? We have 3 sig figs there, 3 sig figs there, 4 sig figs there, and we don't do anything with the unit conversion. So we need to get this thing right here, this answer, to 3 sig figs, which makes it 15.8 right there, right? That's the amount of energy needed. And if we go through and look at our units, we have converted that to kilojoules, right? So 15.8 kilojoules. You might be asking yourself, if this is a dimensional analysis, how are we able to even cancel out the Celsius from here and the grams from here? Where'd that get canceled out? Because the joules get canceled out in the conversion right there, right? Well, if you remember, right, the units right here for the specific heat of copper right here, the 0.385 joules, I forgot to actually put in the bottom part, the denominator part, which is the grams Celsius. So that should be 1 gram, 1 degree Celsius, right? So now the grams cancel out, and also the Celsius cancels out, leaving you with nothing left but the kilojoules. And that's how you get your answer to be 15.8 kilojoules.